All right, we got 8-3, day 2. A couple more word problems here. Nothing really new in terms of what we're doing. Adding these two examples today would just have been a bit much to kind of process all in one lesson, so we split it up over a couple days. All right, an airplane leaves the airport on a course of 120 degrees. Okay, now start to visualize in your head where is it going, okay? Where, in terms of like north, south, east, and west, because I'll always start on my diagram saying, all right, here we go. There's where it started from. There's north, and then I'm thinking, all right, which way did you go, right? And I like those references that east is 90, south is 180. Again, our diagram does not have to be anywhere close to perfect. I'm not going to use quite that much space. But just decent, just good enough, right? That kind of tells us what's going on. Okay, so it went for an hour, so 400 miles, right? And here's the big thing. That angle right there is 120 degrees, okay? And what I have marked there with another reference to north is the point at which the plane is going to change course. It's going to switch its direction. Okay? And it switches to a course of 70. Okay? Now, again, I have my reference point there, and as I'm thinking this through, and maybe you need to, like, make a reference and then erase it. Okay? But I'm thinking, all right, if I were going that way, that's like due east and has a bearing of 90, which we shouldn't be going that far. So it would be like something like that. Ups the speed to 450 miles an hour for 2 hours, so the end result there is going 900 miles to get to here, okay? Now go back to right here when the plane changes course. Always remember, as I'm marking this, the directions that are given are not in reference to what direction the plane was going before it turned. The bearings are in reference to north. That's why every time I mark a new location, I'm like, I got to put a vertical line there representing north, because as I get a new bearing for a new direction, it's always starting at north, and then I'm moving clockwise, okay? There's X, right? You got a big triangle formed. Very similar problem to the one we finished in day 1, right? I've got these two sides, and I'm kind of looking at this thing from this perspective that right here, if I could throw that angle in the mix, what I'm leaning towards doing is going side. If I could get that whole angle right there, which I don't have, then I could use this side, right? Again, similar to that last example in day 1, which ended up as a side angle, side case, okay? Now I'm in luck. This angle right here is 60, right? Coming from the fact that this one and that one have to add up to 180. Put those two together right here. I've got what I'm looking for. That angle is 130. And then we are in great shape. Going to have some relatively big numbers here because it goes 400 miles for one of the sides, 900 for the other. Okay. Again, that whole right side can just go into the calculator at once. Pretty big number. Should get this. Now, the square root sign can get a little bit sneaky, right? It's probably one of the more common cases where you could forget to do it with the law of cosines, that after we did all that number crunching on the right, it gives us the side length squared, okay? Easy to forget to do it. One of the best ways is to just look at your answer and keep the problem in context. The plane went, 400 miles, and then it changed course and flew another 900. Do you think the total journey was 1.4 million miles? I don't think so. I think we need to take the square root, and we would get 1,197 miles. That answer makes much more sense. 400 changes direction to do another 900, went a little bit less than 1,200 miles total to get from their starting point right here to the ending point right there. All right, last one. You're going to see a couple different things on this one. One, it has a diagram, which, in the problems you'll practice from 8.3, you'll get both. Sometimes you'll draw your own. Sometimes you'll get one. The other thing we're going to find, well, actually three things. The directions are given in the north, south, east, west, okay? So we'll go through that in a minute. And the final thing is you're going to see this is going to be solved with the law of sines. And that's possible, right? I want you to have some examples from each that just because you're setting it up like a problem that's got these directional angles doesn't mean we're headed towards the law of cosines. It depends on what information we can get, okay? The bearing from the Pine Knob Tower to the Colt Station, right? Looks like two forest fire spotting towers, is north 65 east. So this whole problem is starting from right here. Right, we're facing north, and you can see the angle right here. We go 65 degrees to the east to get to the Colt Station. Okay, and that distance is 30 kilometers. A fire is spotted by rangers at each tower, has a bearing from north 80 degrees east from the Pine Knob. So go back to our original location. That's right here. Face north, 80 degrees to the east. That's where the fire is. Okay? So we have two different bearings from the Pine Knob Tower. One to the Colt Station, one to the fire. Okay? Now, the last direction that's giving is the bearings from the Colt Station, right? A little bit different deal here is it's given as a reference to south and then goes 70 degrees to the east, okay? Find the distance of the fire from each tower, okay? Now, to get my diagram labeled here, I'm gonna go A, B, C, right? Which is gonna tell me I know side C over here, and here's really what I want. Is as I take a law of sines approach to this, I'm looking for A and I'm looking for B. Okay. Now I need some other stuff. No question about that. I need some more information to kind of make this happen, but A and B is what I'm looking for. Really kind of a sneaky little thing, okay, is right here. This is kind of the key to the whole problem, is that angle is 65, okay? And that's because this line right here and this line are parallel. So you see 65 and 65, those are on opposite sides, and they therefore have to be the same, okay? Huge thing that this does for me is right here, angle B is 135 degrees. That's going to be really helpful. I think I'm going to need that. Okay. Down in the corner right here, I could do 80 minus 65 to get 15. And then over here, 180 minus 135 minus 15. My last one in the corner is 30. Okay, I've got all the angles and I've got one side, right? All the angles and one side. This immediately takes me to the law of sines, right? Because law of cosines only works for two cases, SAS and SSS, okay? Which, if you think about those two cases, to use the law of cosines, you have to have two sides, right? The law of sines is the one situation we have where we could find some stuff if we only have one side, which is our case. All we know is the distance between the two towers, okay? I'm going to start with A. A over the sine of 15 is equal to 30 over sine of 30. Checking on rounding. I don't think it said anything in the directions. I'll just go 100th. You could go 100th or 10th. 15.53 kilometers. Very similar stuff over here to get B, but B has to be over the sine of 135 because that's the angle that's opposite. And then I'll use that same pair of 30 over sine of 30. By the way, that's coming from here and there. My diagram's getting a little cluttered with all my references, but remember with the law of sines, it's always side and angle that are opposite. They always get paired together on the same side. .30 times the sine of 135. Based on the diagram, I'm expecting this. I mean, it says it's not to scale, but I look at the angles. It seems scale-ish, right? It's a pretty accurate situation. I'm expecting B to be quite a bit bigger than A, and it is. .4243 kilometers, okay? That is all for 8-3, day 2. And that is actually our ending point for chapter 8A.